In this video, we are going to discuss about pipelining. It is an implementation technique in which the multiple sections are overlapped in the execution. First, before going to the pipelining, let us discuss about the non-pipelining. What is non-pipelining? For that, I'm going to consider the three instructions, uh, which is a load word, which MAPS instruction, and it has five stages, right? First one is instruction fetch, instruction decode, instruction execution, memory access, and type path. These are the five stages for executing a single instruction in one clock cycles. So let me consider to execute instruction fetch. It will take 200 picoseconds. All the five instruction is taking a average of 200 picoseconds. Okay. So what is non-pipeline ways? After the execution of this single instruction only, the next instruction will get start. So if you see, whenever the to execute the first load word instruction, it is taking 1000 picosecond. Okay, once it get completed, the next instruction gets started, right? So it will start from after the end of the 1000 picoseconds only, it will start. Okay, so it will go up to the end of 200 picoseconds. So the third instruction will start uh, at 200 picoseconds, right? So it will end up to it will goes up to 300 picoseconds. The so the average time between the instruction is 1000 picoseconds. So it starts from zero. It starts from zero and it will go up to 1000, right? So the next instruction will start from here. So the average time between the instruction from this instruction to this instruction is 1000 picoseconds. So what will be the time between the execution of the first and the fourth instruction? So this is taking 1000 and this is another 1000 and this is another 1000. So the time between the execution of the first and the fourth instruction is 3000 picoseconds. So now let us come to the pipelined instruction. Okay. So what is pipelined is again I'm taking the three instructions, load word instruction, and each is taking 200 picosecond. Each stage is taking 200 picoseconds to execute. So this is my first instruction. So instead of waiting for the whole instruction to execute, so it was executing in parallelly, concurrently. So the load word will start from the starting of the 200 picoseconds. Okay. So it will start from the 200 picoseconds itself. Okay, the next instruction will start, right? So this is difference is 200 picoseconds, right? So here also the difference from the second and the third instruction is 200 picosecond, and the third to fourth instruction is again another 200 picoseconds. By this way, it will execute. So if we see the total time which is taking to execute this instruction is the total time taken to execute the three instruction is 1400 picoseconds, right? To execute the three instructions is 1400 picoseconds. What is the time between the execution of the first and the fourth instruction is? So you can see this is taking 200 and this is 400, this is 600. So after the 600 picosecond, the fourth instruction will get start. So the time between the execution of the first and the fourth instruction is 600 picoseconds. Okay. So what is the average time between the instruction? So the average time between the instruction is 200 picoseconds. So the average time between the instruction, these two instructions is 200 picoseconds. Okay. So now let us do the formula. The formula for this one is total execution time of non-pipelined uh, divided by total execution time of the pipeline instructions. So the total execution time of the non-pipeline instruction. So you can see how much time it will take to execute this three instruction. It is taking 3000 picoseconds, right? So that it is taking 3000 picoseconds for non-pipeline instruction, and for pipeline instruction it is taking 1400 picoseconds. So if I cancel these two, so I will get 2.1. Okay, so this is the very less because the formula is this is equal to okay, number of stages. Okay, so this is very less compared to the number of stages, right? Because here the number of stages is 5, but I am getting only 2.1. Why? Because here the I am taking only 3 instructions. So here the number of instruction is less. Instruction is less. So that is why I'm getting very less value. So instead of 5, I'm getting only 2.1. So let me increase the number of instructions. So instead of 3, I'm going for 1 lakh instructions. So if I go for 1 lakh instruction, 1 lakh into 1000, because for each instruction it is taking 1000 picoseconds. So this will be my answer. So already I'm using I have calculated for 3 instructions, right? So for 1 lakh 1 lakh 1 lakh 3 instructions. So 1 lakh 3 instruction, this many time plus 3000, right? 3000 picoseconds. So it is taking uh, uh, these many seconds, picoseconds. Now let me come to for the pipeline instruction. Okay. So here also I'm going to take 1 lakh instruction. So if it is 1 lakh instruction, each is taking 200 picoseconds. Okay. So each one is taking, because the average time between the instructions 200 picoseconds. For each one is taking 200 picoseconds. Okay. So here you can see uh, the 1000 picoseconds to get down to 200 picoseconds, right? With the help of pipeline. So there I have used 1000 picoseconds. Here I have used only 200 picoseconds. So it will be these many picoseconds. So the total time for execution of 1 lakh 3 instruction is this much plus already I have used 1400, right? 1400 picoseconds. So I will get uh, 2 crore 1400 picosecond, right? So now I'm going to apply this formula. Okay, the time between the insertion for non-pipeline. So for non-pipeline is uh, this value, this value. Okay, and total time between the insertion for pipeline one is this one. Okay, so if I cancel this one, I will get 4.99. This is equal. This is approximately equal to 5. So which will give you the number of stages which is I have used in the pipeline. So this pipelining concept will increase my throughput, but it is not increasing my the execution time of the single instruction. So here also the single instruction execution of the single instruction is 1000 picoseconds only. In pipeline or in not non-pipeline the instruction also the time for execution of the single instruction is 1000 picoseconds, but my throughput get increased. So here it is not increasing the execution of single instruction. Now let us discuss about the pipelining hazard. So these are the situation in the pipelining occurs when the next instruction cannot execute in the following clock cycle. So this situation will lead to pipelining hazard. There are three types of pipelining hazards. So one is structural hazard, data hazards, and control hazard. First, let us discuss about the structural hazard. So let me take four instructions, 4 Mbps instruction, that is load word. So it consists of 5 stages, right? Uh, uh, Generally we see the instruction fetch, it will uses the instruction memory, and the memory access will uses the data memory. Generally we have instruction memory also and data memory also. Instead of this, suppose if you are using only single memory for instruction memory and also data memory means, so at the fourth stage you can see at this time, um, the first instruction, this is my first instruction and this is my fourth instruction. Okay, the first instruction is using my uh, using this memory for data, and instruction fetches using this memory for uh, using this memory instead of since don't have the instruction memory, I'm using the I'm having only the single memory. We can't be able to use uh, we can't utilize same memory for both the stages, for both the instruction. Okay, so this will lead to a structural hazard. So this can be avoided if I use a separate memory instead of single memory. If I use instruction memory for instruction fetch and data memory for memory access. So by using that one, I can avoid this structural hazard. Okay. So why the structural hazard means, in this 5 stages, we are using memories in the data path. We are using memories, ALUs and all, right. So if two or more instruction tend to uses same blocks, that is memory at the same time, this will cause us structural hazard. Okay. This may be due to the memory or it may be due to the AID. So I can write the hardware which cannot support the combination of this instruction that are set to execute. So here you can see this ALU will causes ALU, because of ALU the structure of that will causes if the execution stage and the memory access stage both tend to use the same ALU. Okay, so if you use a separate ALU, this will be this hazard will be eliminated. And if I have a limited register ports also, if I use a limited register ports also, this will lead to a structural hazards.